So I've emailed some of you already, but I was going through the like pre-semester survey responses, and I had some of you who did the survey anonymously, but said that you use BMAC. But I couldn't contact you because I didn't know who did the survey. So if you use BMAC to get more time on your exams, just maybe like follow up with them to make sure that they send me an email so I can like make sure I set you up with your accommodations. Um, you'll only get like most people do like time and a half on their exams. That'll only apply to exams, but it won't apply to the quizzes because those are unlimited for time. So you shouldn't have any issues with those. But uh, that was the first thing I was going to say. Oh, for the survey, I had several people, and it's like not an uncommon thing, but if you have like um, problems with like mental health over the semester, please let me know. I personally suffer from like high functioning anxiety and seasonal depression. Like last semester, I was having a really hard time with like depressive episodes and had to email my teachers and was like, I need an extension. I just need one more day to do this because I just haven't been able to like get out of bed. I haven't like I barely am eating. So I know it can be debilitating. So if you have issues like that throughout the semester, just like keep me posted. So that like I can help you help yourself. But I know like our world sucks too, so that doesn't really help with being sound mind. So yeah, if you have any concerns, like if your family dynamic is kind of crazy, if mental health issues, if your work schedule is like all over the place, just communication is better than no communication because I can help you if I know what's going on. So I just wanted to throw that out because there was actually quite a few students who shared those concerns or of the likeness. Um, yeah. For types of data, I sent an email about this like a few hours ago, but I wanted to share this cool picture that I found on Google Images. Let me pop it on the screen really quick. So this is kind of like a nice table that outlines how you can tell the difference between different types of data. So you can see our nominal, ordinal. These two are non-parametric data, and then interval and ratio are our parametric data. Nominal is purely used for labeling, right? So that's why it has this one check mark. The order doesn't matter, and that's its main difference from ordinal data. So I had a couple of questions in the emails about the disease severity example in the practice set of the data classification PowerPoint. And I had listed like mild, moderate, or severe as kind of like my example on what I meant by disease severity. And when I made that example, I was kind of thinking more along the lines of like, oh, somebody takes like the Parkinson's disease scale test and like if you're within a certain range of values, you get categorized as mild, moderate, or severe. Or like if you're doing stage 1, stage 2, stage 3, or stage 4 Parkinson's disease. So when I made that example, I was thinking more along the lines of that. But some of your classmates identified like, oh, if it's mild, moderate, severe, that is also an ordered scale in which the ranking has a meaning to it, because the severity of the disease is progressing with the terms. So that could also be ordinal and not just nominal. The other thing that I mentioned in the emails is like how you collect the data is also going to determine how you classify it. So there was another question on like the membrane potential example, which we identified as interval data because we obviously label it as a variable. It has a meaningful order in terms of like you go from negative, pass through 0, go to positive values. You're not just randomly jumbling numbers around. There is a measurable difference because they are quantities that you collect, right? But it doesn't have a true 0 starting point, or it doesn't have like the absolute 0 concept that we talked about last week. So I liked this figure because it used this wording, true zero starting point. So interval data, remember, doesn't have it doesn't have to start at zero, right? So we can assume negative values, we can assume positive values, and we can assume a zero value in between. So the membrane potential example would be a good example of interval data, because the resting charge of the inside of the cell is negative. As soon as you hit it with an action potential, right, that's going to change the channels like that open up. So you introduce more positive ions into the center of the cell, which cause the charge inside of the cell to rise past zero into a positive zone. Another example of like differences between interval and ratio, someone had asked about force, because force can assume both positive and negative values. The way that you describe it is going to be if it's interval or ratio. So if we were talking in terms of force in general, so like if I stood on a force plate, from me, the force that I exude on the ground, if I'm in the air, starts at zero, right? Because if I was elevated off the ground for some reason, I was going to make a Harry Potter joke, but then decided not to. But if I was levitated off of the ground, I am exuding zero force down into the ground. As soon as I stand on the ground, I have a zero starting point, right? So that kind of goes along with this table here. I have a zero starting point of the absence of force. And then as soon as I step on the ground, I have a negative force that goes into the ground, right? Some people might confuse that with the vertical ground reaction force from the ground pushing back at me. Still a zero, right? Because if we have a force plate just sitting as a force plate, the force is zero on that force plate. As soon as somebody steps on it, it will read the equal and opposite force that the ground is pushing back up on us. So in that case, zero is the starting point for both force from my perspective as well as force from the ground, which is why force is a ratio measurement. I think another question popped up as like, well, what if we're looking at net force? That would be an interval measurement, right? Because net force can, if you have vector quantities that have both magnitude and direction, right? You may have equal and opposite, like if like tug of war, if two people are equally and oppositely pulling on a rope and there's like no movement of that rope, you have a net zero force being exuded on the rope, right? So in which case zero is not a starting point anymore. It's not the absence of a measurement, but rather it's a real value that exists within a scale of negative to positive values. So I hope, did that clarify stuff for anybody? You can use chat responses or participant reactions, thumbs up, down, yes, no. But I posted this in Beachboard in the module 1 checklist next to the data classification game. And then I also put it in the supplemental materials folder. So you guys have a couple of different places to find it. All right. Any questions on that stuff? Sweet. The only other thing I wanted to say is stuff on discussion format. Some people are like, do I do it in a bullet list? Do I do it paragraph, essay format? As long as I can find everything that's in the rubric, you should be fine. I sent an email about that. So this is also a good opportunity to see if emails have been working or going through to you guys. So if you didn't read that yet, try to look for it in your student email. And then let's pull up our lecture. So today is another one of those foundational topics lectures. I'll try to keep my eye on the chat and participant view so that I stay with you guys in terms of speed and everything. But the first part, we're going to talk about measures of central tendency and variability. Most of these calculations you guys have probably heard of before, either in like just regular algebra, or if you've taken like more of like a general statistics course prior to this. But we'll talk about those in the first part. We'll take a short break, and then we'll talk about the normal curve, or a bell-shaped curve. The hard part with this today's lecture and next week's lecture is I can't introduce one thing without talking about everything. So we're kind of gonna be skipping around a bit. Because the measures of central tendency and variability are kind of critical to building a normal curve. But we'll talk about the normal curve in the second half of the lecture. So we'll try doing the simpler stuff first so that I don't fry your brains. Yay. We love this class. All you need is love. False. You need to read and take notes. Also, The Office is a great show. Okay. So I'm going to start now and stop being dumb. Okay. So the normal curve, just so you have an idea of what you're looking at, or if I say normal distribution, bell-shaped curve, distribution shape, whatever, right? Whenever we talk about the normal curve, this is what it looks like, right? So it's shaped like a bell. But this is generally what we assume the shape of a sampling distribution of a population to look like. And what a sampling distribution is if we were looking at a research question and we said, I'm going to take this sample, this sample, this sample, this sample, this sample, this sample, this sample. We're taking basically like a very, very large number of samples that have their own statistics, and we plot those sample means on a distribution. The sampling distribution of a population should be normal, or should look like the graph you see in front of you. The central measure that we use in when we evaluate distribution shape is the mean, which most of you have heard of before. We used it actually in our activity last week. And then the variability measure that we use in the normal curve is standard deviation, which is denoted by the little baby sigma in this picture. But we'll kind of come back to what the shape means and how we evaluate shape a little later, just as an introduction. Some of you have probably heard of skewness before, at least the more common one. Kurtosis is another way that we can look at shape. But the actual shape is going to be assessing if you have outliers or any extreme scores in your distribution. And the next lecture will kind of cover how you identify those outliers. So this is kind of just a very basic introduction. We'll go more in depth after we talk about our measures. So measures of central tendency are going to describe the middle or central characteristics of a set of data. The three that we do in this class are the mode, the median, and the mean. And we'll talk about each of these individually. But basically, if we had, like you guys actually did, you made frequency distributions last week on like pull-up data, right? We can say how many people are able to get a certain value in our range of our variable that we're interested in, right? So that variable would be on the x-axis, our frequencies are on the y-axis. And if we have a nice, beautiful frequency distribution like this one, we can overlay a curve on top of it, right? And so that is the normal curve we'll be talking about. But you can see in the center, that's where we have the most frequently occurring, or where our data is more concentrated. So our measures of central tendency kind of give us these ideas of where peaks are located if we're looking at more simple frequency distributions. Okay. So each of those individually, the mode is going to be the value in a data set that occurs the most often. So if we create a frequency distribution table, whether it's simple or grouped. You guys did both of those last week. Simple being you start with just a raw score, like how many people were able to do 3 pull-ups, and then you gather the frequency for that value. And then you do 4, and then 5, and then 6, and so on and so forth. So that would be a simple frequency distribution. The grouped frequency distribution you guys did was on the relay race, and you had a 5-minute interval, and how many people finished within that 5-minute interval. That would be an example of a grouped frequency distribution. In either case, you can look at the frequency column that you calculate using your COUNTIF or COUNTIFs functions, and you can see whatever the highest number is, that is the mode of your group is going to be associated with that highest frequency. So oftentimes we'll use those frequency distribution tables to help calculate what the mode would be. There's also a function in Excel. Yes, so you can calculate it really quickly if you have your entire set of data to pull out. It's also important to note that you can have multiple modes in a data set. So when you have 2 modes, we call that bimodal. If you have more than 2 modes, that would be multimodal. But that's if, like, say our highest frequency in occurring in a data set was 10, but there were 3 values that had a frequency of 10. That would be like a multimodal distribution. So that's what a mode is, most frequently occurring value. The pros to using a mode is that it's really easy to determine, right? You do your Excel function or you create a frequency distribution table and bam, you've got the highest, like the most frequently occurring value. It's also a very quick estimate of the center of a group of data. So generally where the peak is where the center should be, unless you have like an inverted bell curve or a bimodal curve where you have peaks on the outsides of your distribution and the middle is where it's low. But generally speaking, it's a very quick estimate of where the center of your group is. And it's also a fair description of central tendency when your data is normally distributed, which should make sense because if we go back to this slide, in a normal distribution, the most frequently occurring values should be in the center. Okay. In terms of cons, it is what is known as a terminal statistic. So this means that after you make that calculation, it's not involved in any other calculations. So if we calculate a mode, all we have is a mode, and we can't use it in any further statistical analysis. It also disregards extreme scores, right? So if we're looking at a distribution that looks like this, and let's say we have an extreme score out here, if all we're looking at is the most frequently occurring value, we have no idea that that score exists in the end of the distribution. So modes are good, easy to determine, very quick estimate, but we can't use them in any further statistical calculations, and we don't know if extreme scores exist in our distribution if we're relying on the mode as our main measure for central tendency. Question so far? Let's make sure. Cool. Okay. I don't know why I started hyperventilating, but yeah. All right. Our next measure of central tendency is the median. So this is the score in the middle of your data set when your data are rank ordered. So meaning you list your values from smallest to largest, then you find the middle value. Excel also has a function for this. Yay! So it's pretty easy to calculate. One thing to note, if you were doing this by hand, is that when you have an odd number, n being your sample size, so you have an odd number of scores, the median is the exact middle value. If you have an even number of scores, then you take the average of the 2 middle values. In other words, you add them up and divide by 2. Okay. Pros to using a median is if you have ordered data or highly skewed data. So if I toggle back to this graph again, let's say that instead of me having this perfectly symmetrical distribution, my peak is actually over here, right? regardless of where that peak is, the median should still be able to reflect where the middle of that distribution is. So it's nice when we have skewed data because it's primarily looking at the quantity of scores and not the actual quantity of the values that we've collected. So in that case, it's not affected by extreme scores because we're literally just finding the middle value in the distribution as far as our calculation goes. However, extreme scores are also disregarded, right? Because it's, again, we're looking at the order of the values. And so if we're only looking at the center or middle value, we don't know if there's an extreme score below our mean or if there's an extreme score above our mean. So it's not affected by extreme scores, but it also disregards them. So both a pro and a con. Similar to the mode, the median is also a terminal statistic. So once we calculate the median, that's all we have. We can't use it in any other calculations. And then we have the last measure of central tendency, which is the mean. This is the arithmetic average of scores. So you have a data set, you add up all of the values that you've collected and then divide by the sample size. Again, you guys have used the average function in Excel already, so you know it exists. But the nice thing about the mean is it considers both the frequency and the quantity of scores, right? So kind of puts the pros of using a mode and a median together. But it's the most commonly used measure of central tendency because it is sensitive. So you'll recall that the cons of the mode and the median is that they disregarded extreme scores. The pro for using a mean is that it is sensitive to extreme scores. So if we have values that are listed, actually I have an example on the next slide, so I'm not going to give you an example now. But if we have an extreme score on one end of the distribution, our mean is going to get drugged towards that extreme score. So in that case, it's sensitive because we can detect if there's an issue. It considers all aspects of our data. So we're adding up every single data point instead of just picking out what's the most frequently occurring data point or what's the data point in the middle of our distribution. It provides a basis for further statistical calculations. So a mean is not a terminal statistic, right? We can continue to put a mean into a t-test or an ANOVA so that we can see how means of different groups are actually different from each other. It's also most appropriate for ratio and interval data. So data that have like actual numerical quantitative meaning to them. Con of using a mean, however, it's sensitive to outliers, but it can be very negatively affected by outliers. So in terms of the calculation, at least. We'll talk about how we can test for outliers in our next part of our lecture. But that is something to keep in mind. If you have an outlier and you haven't detected it in normality tests, then that's very problematic for your mean. Okay, I'll do 2 more slides and then I'll check in with you guys for questions. So this is just a practice for you to calculate mean, median, and mode. I recommend you use Excel to do this. And I have a video that's linked in here. I was playing around with this earlier and thought actually, like before I went on my trip, I was like, I didn't make the videos. If you have this open just like in regular PowerPoint, you're not in presentation mode or anything, if you right click on this, like, because initially it'll just look like blue underlined text. But if you right click on it and choose to open the hyperlink attached to it, then it works. But I was convinced I hadn't made the videos. But anyways, I kind of walk you through how you can calculate the mean, median, and mode using Excel. When we have a table that looks like this, it's a simple frequency distribution. But basically, the value that you're inputting in your ordered list is the number of pull-ups in this particular scenario. The frequency is how many times that number happens. So if we're in Excel, we can see 2 people performed 1 pull-up. Our order that if we're making a list would be 1, 1. We can see that 5 people completed 2 pull-ups, then we do 2, 2, 2, 2, 2, 2. I think I said that 5 times, right? And then you would have 11 threes, 9 fours, 8 fives, so on and so forth. Some people, when they see the frequency distribution table, they put, they flip-flop what I just said. So just make sure you have it straight. Like the frequency is how many times this value is occurring in this column over here. Okay, but I'll give you guys practice. You can calculate the mean, median, and mode using functions. So if you want to attempt the activity first, where I go through step by step, and then you want to try this practice problem, that's another great way to do this. And then you're going to create some type of visualization by means of a line or a bar graph to represent your data. And you should get something that looks like this. So the solutions are on the next slide. In a normal distribution, usually we would expect the mode, the median, and the mean to be in the same location. So in other words, they'd all have the same value assigned to them. In this case, that didn't happen. And the reason being is that you can see there's this extreme score of 25, right? So this is a great example to show you guys how outliers affect these measures of central tendency, or rather how they don't affect the mode and the median. Okay, so the mode is still the most frequently occurring value, right? Which we can see is pretty centered with the peak. In this case, our mode would be 3. We can also visually see that in our frequency distribution table because it has the highest frequency attached to it. If we ordered all of these in a list from 1 to 25, with their respective frequencies, and we found the middle value, that should have been 4. So generally pretty close, again, like rough estimate of where the center of the distribution should be. And then the mean, when we calculate this, it actually ends up being 5.1. If we calculated the mean without this extreme score, it would probably be closer to a value between 3 and 4. So when we have extreme scores, because you're adding every single data point, that this extra 25, right, is going to significantly inflate the sum that is in the numerator of our average calculation. So that's an example of how extreme scores are, or our mean is sensitive to extreme scores. It's going to get drugged towards wherever the extreme score exists. Okay, just also to note, if you're in PowerPoint, the answers are in the notes section. So if you don't have that expanded when you're reviewing these slides, if you want the actual number answers, they're in that area of the PowerPoint. Okay, I'm gonna pause for questions. You can do chat or just yell at me. Median considers the, so I'm going to read the question for people who watch the recording. Does the median only consider the quantity of scores or both frequency and quantity of scores? So the frequency is in terms of how often do the scores show up. That's related to the mode. The median looks at the number of scores. So I guess I have to be careful with wording, because quantity of score could also be like, what is the numerical value of an individual score? So the quantity of scores in the wording that I chose is like, how many values are there in the distribution? That's what the median considers, right? How many values are there and where's the middle of that, of those quantity of scores? So if we have, 20 values, what's the middle of that set? In terms of the mean, that acknowledges both the frequency, so how commonly a value will show up, because if that number is repeatedly added in an average calculation, then it's going to draw the mean value towards that value that's repeated. So it considers frequency, but also considers the quantity of how many scores you have, and also the actual quantity of an individual score. So that plays into the outliers comment that I made. Did that help?
Kind of actually. I'm just gonna ask it like through the mic, but because I actually did this and I was asking if it does consider both the quantity of the scores and frequency, just because when we do this on Excel, I know it considers the amount of times that it kind of occurs, right? So that's why,
Mm-hmm.
like, yeah, I wasn't sure. So,
Yes. So I would say it like wait, so is your question specifically just about the median then?
yeah,
Um, so that one would just be the quantity. The
okay,
frequency, if it happens to land in the area where there is the highest frequency of values, then that's great.
okay,
Yeah. Uh, but I would say median is more along the lines of the quantity or number of scores and less on the frequency part.
okay. And when you say quantity of scores, it's just
Like,
it's not exactly like the numerical value, right? It's just
yeah, it wouldn't be
okay,
like, what's the quantity like the 4 pull-ups? Not talking about quantity in that way, but quantity like if we added up all of the frequencies, like how many scores did we have, or like the sample size.
oh, okay, got it.
Yeah,
Yeah, thank
yeah.
you.
Because then we take those total number of scores and we just find the center of it. Yeah. Um, One asked a question, why would the median be appropriate for skewed data? Um, you answered your question actually. It's the median is appropriate for skewed data because it's not sensitive to outliers. So um, in this example, our median was 4, kind of landing right about here. And that's still relatively in the center of where our peak should be. So because we are counting where's the exact middle, it doesn't matter if there's this 25 on the outskirts of our distribution. That doesn't go into the calculation of the median at all. Is that cool? I got a thumbs up. I don't know who gave it to me though. Sweet. Oh, Juan, got it. Awesome. I really need to get a second screen. I have like chat and participant windows like covering the slides, so I have to move them around a lot, but okay. So those are our measures of central tendency. We'll go to measures of variability now, which are going to tell us how spread out our data are. The other way, I like to use spread. Some people prefer the word dispersion because it sounds more academic, apparently. But variability, how much does your data vary? Varying compared to what is kind of up to the type or the type of measure that you use. But in our class, we have 5. The ones that you're going to use the most often in the class are going to be interquartile range. That's simply because we use this calculation to look at outliers. Standard deviation is going to definitely be the most common one that you use in this class, but I like to mention the other ones too, just because they are important to know about, especially if you have data that are not normally distributed. A lot of times you might see someone who, instead of a mean and standard deviation that's presented, they show a median and an interquartile range. Or if we're looking at a variety of variables that have different units and we want to compare like which one varied the most, we might use a coefficient of variation. So each can be used in its own respect, but they're all valid in their own right. The range is the easiest one to calculate. You literally find the minimum and the maximum and you take the difference between those two values. Okay, so you guys actually do this in activity 1 when I say like, oh, make a list of values from the minimum value to the maximum value. what's the range of the data, right? Maximum minus 10. So we like that because it's quick and easy. Yay. It's a rough estimate of the spread of data. And we say rough estimate because if you have an extreme score, then your range has been impacted. So example being, if we look at this distribution, right? In terms of the values, the minimum value of number of pull-ups would be 1. The maximum would be 25. So if we were just looking at a range based on those two values, we would say, oh, our range in our data was 24. 25 is an extreme score in this case. So if we actually had a maximum of 10 pull-ups and a minimum of 1, you can see how we go from 10 minus 1 is 9, which would be a more accurate description of the range of data compared to if we included the outlier, which would give us a range of 24. So that's just an example of range is a rough estimate, but it is nice and quick and easy for us to calculate. So that's our first measure. Our second measure is the interquartile range, also commonly referred to as the IQR. And this represents the difference between the raw score that exists at the 25th and 75th percentile. Okay, so we take the difference between the raw scores that exist at these two percentiles, and that gives us our interquartile range. So in other words, we get the range of the middle 50% of our data. Now we'll talk about percentiles next week, which is, again, it's just so hard sometimes to do these lectures in an order that makes sense. But percentiles, some of you have probably heard about percentiles before, but it's a scale from 0 to 100. And usually when we're talking about a percentile, if we have a variable in the x-axis, we organize that variable in such a way that the worst scores are on the left side of our distribution and the best scores are on the right side. So if you've taken a test, or like if any of you have taken the GRE, we actually have a discussion on the GRE next week. But if you've taken the GRE, when you get your test results back, it'll tell you what percentile you scored in. And so basically that percentile means you scored at or worse than the rest of the people who took the test who got that score or worse. And that becomes your percentile. So when we create an interquartile range, we have to talk about different quartiles. Quarter, you think 4. There's really a 0th quartile too, but it just represents the minimum of the data. Q1 is the 25th, so that goes in here. I just saw a chat pop up, which I will address in a second. Q2 is the 50th percentile, which is usually going to be associated with the median value or the middle of the data set. The 75th percentile is associated with Q3. The 100th percentile is associated with the maximum value in the data set. So again, interquartile range, we take the difference between the value that exists at Q3 and subtract the value that exists at Q1. Let me look at the chat really quick. Got it. Acknowledged. Okay, it wasn't a question to shout out to the class. Okay, so pros to using interquartile range, it's a good indicator of the spread of the majority of the data. I will skip back to an image that we showed of our normal curve because we get the middle 50%, right? Difference between 75th and 25th percentile is 50%. And if you look at our normal distribution, assuming we have a normal distribution, the middle 50% pretty much exists between one standard deviation above and below the mean. So generally we should get a good idea of how spread out the center of or the majority of our data is. And now I gotta find the slide again. So good general indicator of the spread of the majority of the data. It's not influenced by extreme scores because of the picture I just showed you. If we're only looking at the middle 50%, we're disregarding anything that exists way out in the tails of our distribution. It's often used with ordinal data and highly skewed ratio or interval data for the fact that it's not sensitive to those things. So similar to how we would use a median when we have highly skewed data, that's why medians are usually paired with the interquartile range if they are reported for non-normal distributions. But ordinal data is also a nice one because we're still looking at the middle 50% of the ranked values that we have accumulated. So that's the interquartile range. Variance is another measure of variability. And this looks at the average of the square deviations from the mean. It's a lot easier to explain what that means if we look at the formula. So this large sigma E looking symbol, this big sigma, if you're in Greek life, you probably know that already. But that means sum or a summation of whatever follows it in a formula. So you guys don't need to memorize this one. I'm just using it to explain what variance actually measures. So X is going to be some raw score from our data. Mu in this case is going to be the mean. Note that this is a formula for a population. So we're going to say population mean. So what the numerator does is we have some raw score and we find how deviated it is from the mean or what's the distance. Okay, so if we have a value that is less than the mean of our data, we should end up with a negative deviation. If we have a value that is above the mean, we'll end up with a positive deviation. Okay, and that's just regular subtracting rules, right? 10 minus 5 would give you a positive deviation versus if we had 5 minus, or not, don't use the same number, Natalie. If we had like 3 minus 5, that would give us a negative 2, which would be a negative deviation. Okay, so in general, this subtraction part is going to tell us how deviated our raw score is from the mean. And then we square that value and then add up all of the squares, right? And then divide by the sample size. So when we look at a regular average calculation, you add up all of your values in your data set, divide by the number of those values. That's basically the average setup. We're dividing by the number of values that have occurred in our sample. And we're dividing that by the squared deviations from the mean. So to put in a formula perspective, that's what we're doing. When we take the square, this is called the sum of squares, this whole top part here, because you're summing a bunch of squared differences. It makes sense. But what this does is it eliminates the influence of negative values. So for those of you who've taken 312, which should be all of you, if you guys remember the long jump example, when you looked at absolute error versus constant error versus variable error, I think is the other one. You'll remember that absolute error is like, how much did we deviate? Doesn't matter if it was below the mean or above the mean. We just want to know how much deviation occurred. Variance is very similar to that. Okay, so we just want to know how varied is our data from a mean value. As an example on how you can practice calculating this, we need 3 pieces of information. So our mean of our population, a raw score of interest, as well as the sample size. So I just made this up. But if you want to do it calculations by hand to make sure you kind of understand how the formula works, we would take our first value in our data set, so 12, which would be X, minus 21, which is our mean, right? And we get a negative deviation because 12 is less than 21. So negative deviation, meaning we're below the mean, right? And we do that for every single value in this data set. So you can see we have both negative deviations as well as positive deviations. We can square each of these values. So 9 squared is 81, right? On. Then we add all of these squared values together to kind of put our numerator as like put it together as a whole. And then we would divide by 8. So 292 divided by 8 would give us our variance, which is 36.5. Now, variance is going to be expressed in the units of what you're measuring. So if this was vertical jump height, we have a mean of 21 with an absolute because it's a positive value, right? Variance of 36.5 inches. Okay. Variance isn't going to be a very commonly used measure of variability in our class. We like to use standard deviations, which are very similar to variance because in terms of the calculation, it's this all the same, but we take the square root of it. So when you see, if you guys remember from basic algebra, when you take the square root of anything, your answer is always plus or minus, right? So the square root of 25 is plus or minus 5 because anything squared is always going to be a positive number. So reverse that, you have potential to have both positive and negative answers when you take a square root of something. So when we do the square root of the variance, that ends up telling us how much deviation we could potentially see above the mean as well as below the mean. And then some of you have probably heard 1 or 2 standard deviations or 3 standard deviations from the mean. That's basically saying take the standard deviation if we're looking at just one deviation, either positive or negative, above or below the mean. If we multiplied that deviation by 2 or 3, that ends up giving us what our values are at 2 or 3 standard deviations from the mean, either going up or going down. So standard deviation is preferred usually because it's a smaller number. It's a lot easier to interpret than using variance. But you can see our variance calculation or variance formula is simply divided, right? Or not divided. It takes the square root of it, and then we can represent our standard deviation as a plus or a minus 6.04. Okay. And I didn't put the plus or minus, but I probably should have. Okay. One thing I want to note about the standard deviation and the variance formulas I just gave you, I noted in each of those slides that those are population calculations. And this brings us to talk about what degrees of freedom are. That I hate statistics and motor control because, or not motor control. Well, yeah, it could be motor control. It also is biomechanics. All around, degrees of freedom has 2 different meanings in both contexts. Okay, so when you guys have like taken your biomechanics or motor control classes, we talk about degrees of freedom as the number of ways that your limbs or a single joint is free to vary, right? So when we talk about the shoulder, it has 3 planes of motion. Therefore, it has 6 degrees of freedom, right? Flexion, extension. Well, technically 3. It kind of depends on how you describe your degrees of freedom. But the degrees of freedom are explaining how many different directions can our shoulder move, right? We have rotation as well. Degrees of freedom in the sense of statistics is not talking about joint motion whatsoever. So in this case, degrees of freedom is used as a correction factor. And the reason why we need this is because when we talked about this last week, we're usually dealing with samples when we're looking at statistics. We rarely ever have the entire size of the population. Therefore, we use degrees of freedom to kind of account for any error that might have occurred in our sampling process, right? And so because we have to assume, right, that our sample, we can't assume that the sample is equal to the size of the population, we add in, for these two specific examples, we add in an n-1. When we look at degrees of freedom for t-tests or for ANOVAs, like later in the semester, the degrees of freedom calculation changes. I'm so sorry, I didn't make the rules, but we'll talk about that later. But degrees of freedom changes, it's just a different correction factor that has different rules applied to it that accounts for the fact that your sample is smaller than your population. So that's what its purpose is. And we can see that if we look at, or if we did these calculations with this formula on the same set of data I showed you 2 slides ago, originally for our population values, we had 36.5 as our variance and plus or minus 6.04 as our standard deviation. When we account for the degrees of freedom, or this n-1 in the denominator, we end up with the purple values, which is 41.7 and 6.46, okay, for variance and standard deviation respectively. And you can see that these values are larger, right? So we end up adding some degree of error to account for the fact that we haven't sampled our entire population in our sample of people that we collected. Okay, so it's a way to build in error. It kind of ends up making it harder to usually prove significance, but it's better in the long run because it makes your research or the results that you present a little bit more sound, so that they account for the fact that you didn't sample your entire population. That's literally why we use them. That's the only reason. Okay, but it's not varying joints in your body or different ways that you can move your body. So I always have students who get confused. They're like, but degrees of freedom is this. I'm like, it is both. Whoever did stats and Kin, they did not see eye to eye on that. So I apologize on behalf of them to you guys about that. But are there any questions on degrees of freedom while we're still on this slide? Chat or participant, raise hands, yell at me. Sweet. Okay. All right. Our last measure of variability is the coefficient of variation. It'll also be written as COV. I've actually seen this one pop up in research a little bit more than I thought I would in reading so far. But it is a way that we can normalize standard deviations or other measures of variability. I don't need that notification, thank you. So if we collected variables on a sample and each variable has a different unit of measurement, coefficient of variation is a great way to assess the variability between each of those measurements. So I've given you an example. The formula for both a sample and a population is just looking at the standard deviation divided by the mean multiplied by 100. So coefficient of variation is going to be represented as a percentage. Or we can say it's the percentage of variability that's within the unit we've measured. So I've given 2 examples. Let's say we collected VO2 max. We got a mean of 60 milliliters of oxygen per kilogram per minute, and we had a standard deviation of 6 milliliters per oxygen per kilogram per minute. Okay, so standard deviation is also in the units of your measure. Okay, I also measured peak power output, and let's say that I got a mean of 1400 watts with a standard deviation of 200 watts. Great. How do these measures like compare to each other, right? So if we did 60 divided by 6, so I'm just using my formula here, 60 divided by 6 times 100 is going to give me 10%, right? If I did 1400 divided by 200 times 100, I would get 14.3%, right? So now we have found a way to normalize or create a standard score such that these different units of measurement are now on the same scale from 0 to 100%. And then we can evaluate which of our variables varied the most, right? So the way that we do that is we say which percentage is higher. Oh, it's so easy, yay, right? So we could say power output had greater variability in its set of data than VO2 max had in its set of data. Right, so lower percentage means less variability, higher percentage means more variability. Let me see. I don't think I had any other notes on that. So, any questions on any of our measures of variability? Chat participant.
Going back to IQR,
Yeah.
Will we have to calculate what the 25th and 75th percentile is, or will that be given to us typically?
You will calculate it.
Okay.
Yes. And I go through examples of how to do that in the activity this week. There's actually 2 different Excel formulas you can use. So it's kind of pick the one you like and then run with it. But yeah, usually you guys will have you'll have just the list of data, and then you have to piece together your calculations most of the time. Yeah. Any other questions on this thing? Oh, I just saw a chat. You said something about adding degrees of freedom for error. Can you repeat it? Oh, degrees of freedom just accounts for the error that you get from not sampling your entire population. So I don't know if I said it the exact same as I did like 5 minutes ago. But you'll get larger degrees of variability, or you'll get larger quantities of your variability measures, because the n-1 in the variance and standard deviation calculations is taking into account that you haven't gathered everyone in your population. That was probably closer to what I said. Another question. Going back to the measures of variability slide, is the data depicted in the graph representative of positive or negative kurtosis? Jumping ahead, I see. This would depend, because these graphs are looking at how spread out the like the red, the green, and the blue areas are. So it's more or less like how wide is our deviation from the mean, and less about what our outliers are, if that makes sense. We'll talk about kurtosis and skewness in our next part, but I see how you're thinking ahead. If Neil, you probably thought like this is positive and this is negative, but because we don't have any numbers attached to it, we can't really argue either. Yeah. Okay.
So variance is just like standard deviation is variance, just a square root of it. So it's kind of like a process from range to interquartile range, and then variance, and then standard deviation, and then COV.
Yeah. Variance and standard deviation are the only ones that are like super related to each other, though. Standard deviation being the one that we would use the most commonly if we were pairing it with a central tendency measure of a mean. So mean, standard deviation are usually what you'll see in research if you have normal or normally distributed data. If you don't have normally distributed data, the next most common thing that I've seen is a median and an interquartile range. I don't actually think I've ever seen variance reported because most people use standard deviation. I don't think I've range, maybe I've seen a couple times, but that's just to say like, oh, our data ranged from this value to this value. Okay, cool. You don't really get a whole lot of information from that, but yeah. Coefficient of variation is its own thing. So it's a standardized measure of variability. Yeah. Does that answer your question? I'm not really sure if I did.
Yeah.
Okay. All right. Any other questions? Jumping back to the first half. Go over the difference between a sampling distribution and a sample distribution and a sampling distribution. Oh, we'll actually go over this when we do our normal curve in the next part. But that's a very good question. Always something that is like, I don't know. Yeah. Okay. Let's take a 5-minute break and we'll come back at 5:10. So go pee, get something to drink, take a nap. 5-minute nap. So restful. I'm gonna stop recording. Stop recording.